So we talked about the mechanism for an unreactive carboxylic acid derivative and a basic reagent. And that was one of the three kind of classic mechanisms that you're going to be seeing over and over again. Another one that you're going to see a lot of examples of is a reactive acid derivative, by which I kind of mean acyl chlorides and anhydrides. Those are the two most reactive acid derivatives with neutral nucleophiles. And you've already done an example of this in general chemistry lab in the first semester, where you took acetic anhydride and you reacted it with salicylic acid. And you made from that acetyl salicylic acid also known as aspirin. So the mechanism is very similar to the mechanism for saponification. The difference being we have a carbonyl group that has a much larger partial positive charge on it because we've got a nice electron withdrawing group. And we have a great leaving group because the leaving group now is acetate ion. And acetate ion is resonance stabilized and therefore a much better leaving group than the alkoxide or amide ion that we lost in the previous step. The mechanism is still going to be an acyl addition elimination mechanism where we do the addition in the first step and the elimination of the leaving group in the second step. But now, even a neutral nucleophile is good enough to react with this more reactive carbon. Carboxylic acid groups on the salicylic acid is just along to the right. Because the nucleophile is neutral, our intermediate is neutral. We have a negative charge on the anhydride oxygen, and then we have a positive charge on the oxygen that just attacked, which now has 3 bonds to it. That's a reversible step. That's the nucleophilic attack. I should actually write that here. That's the overall reaction, not the mechanism. And now we're going to have a loss of the leaving group. When we come back in, and in principle that's reversible. But in practice it isn't really because the acetate is so stable that it's unlikely to come back in. Okay. My card being on the wrong side. So now we have a positively charged intermediate. where this hydrogen is still attached to a trivalent oxygen. So we're going to have a proton transfer step where the acetate ion comes through and grabs that to generate the final product. So the other product is acetic acid. That acetic acid came from this circle group. So you should recognize this as fundamentally the same reaction. Nucleophilic attack in step 1, loss of the leaving group in step 2, and a proton transfer in step 3. But these are positively charged intermediates instead of neutral intermediates because we started with a neutral nucleophile. That's a good proton transfer step, right? This is highly acidic because it's trivalent. It's not as acidic as hydronium ion H3O+. It's actually slightly more acidic because we have these partially positive carbons that are drawing electron density away to make that acid stronger. So that's a pretty irreversible last step. The pK of this hydrogen is 5, and the pK of this hydrogen is less than -2. So that equilibrium constant on that third step is going to be greater than 10 to the 7, which means we're writing it as an irreversible step. So again, the first two steps are equilibrium, but the last step, that proton transfer, is effectively irreversible because of the great difference in acidity. So you ran this reaction in general chemistry. It's not limited to the anhydrides. The same mechanism can go on acid chlorides. So if I were to take benzoyl chloride, and I were to react benzoyl chloride with an amine, in this case, a secondary amine, dimethylamine, I would expect that nucleophilic lone pair on the nitrogen to be able to attack the carbonyl carbon. Charge separation in our intermediate, just like we did with this one, where the nucleophilic atom now has a positive charge on it, and the carbonyl oxygen has a negative charge on it. We've gone from our sp2 hybridized carbon here to an sp3 hybridized carbon here, which is standard for all of these nucleophilic acyl substitution mechanisms. And now we're going to kick out the leaving groups, chloride. In principle, that's a reversible equilibrium. But in practice, chloride is a pretty poor base and a very good leaving group, so it's not really likely to reverse. After that elimination step, we have a positively charged product. And we just need to remove that proton. What's going to remove that proton?
The chloride?
The chloride is the wrong answer, but I was trying to sucker you into that. Chloride is a terrible base. HCl is a really strong acid. So in the presence of an amine, you're not going to have any HCl. So what's going to remove that is the second equivalent of the dimethylamine. You were supposed to give me that answer, by the way.
Oh, them. I thought I'd just play along nicely.
That was the answer I was looking for.
I mean, it didn't seem right because you're like, it's a terrible base first. And I'm
Terrible
like, you know, maybe just, I think he wants me to say that.
And so then the other product is dimethyl ammonium chloride. It's important to understand that the base that's going to take that hydrogen off is this dimethylamine though, because that will help you understand that you need two equivalents of dimethylamine or this reaction isn't going to go well. Right? You can't make chloride take that hydrogen off. It will say no. So you're going to waste half of your, if you only had one equivalent, you'll waste half of your amine deprotonating it, and you'll only get a 50% yield. So we need two equivalents of these. Frequently, when you have a large complex acid chloride that costs a bunch of money, you just bathe it in a vast excess of dimethylamine, which is cheap. You can even use dimethylamine as the solvent for this reaction if you've got plenty of it, and then you can recover it later by distilling it. So, same mechanism, nucleophilic attack, elimination of the leaving group, in this case chloride, which is an excellent leaving group, and then a proton transfer, using whatever the best base is that's in solution. Right? So you want to make sure you're using the best base, not one of the bases that's weaker. Lots of things can be added to acid chlorides. Because the acid chloride is the most reactive derivative of the acid derivative, you can go downstream and form esters and anhydrides from it as well. So acid chlorides react with carboxylic acids form anhydrides. Acid chlorides react with alcohols, form esters. And acid chlorides react with amines, as we've just seen, form amides. As you go from the acid chloride to the anhydride to the ester to the amide, you gradually decrease in reactivity. So the anhydride can be converted to the ester, as we've just seen, by reacting with an alcohol. And the anhydride can be converted to the amide by reacting with an amine. Right? Anhydrides are reactive enough to react with neutral nucleophiles to go to the less reactive material. Esters can be converted into amides, but not using neutral amines. The ester is not reactive enough for the neutral amine to go. Right? To get an ester converted to an amide, we needed to use the amide ion, the basic reaction, which was number one. Right? So these are all examples of neutral nucleophile, reactive acid derivative, three-step mechanism where we have a nucleophilic attack of our neutral nucleophile, followed by the loss of a good leaving group, either a carboxylate salt or a halide, and then a proton transfer step at the end. So let's look at an example of an acid chloride. This acetyl chloride in this case is reacting with a carboxylic acid. Carboxylic acid to form an anhydride. If you were asked for the mechanism of this, where would you begin?
The electrons on the alcohol. Oh wait, did I just say something wrong?
No. I'm just applying great rule of organic chemistry number one, which is when you're in doubt as to what's going on, draw the minor resonance forms. And the minor resonance forms can often be your key to understanding what the reaction is. Your job is to get the best nucleophile in the system together with the best electrophile in the system. That's always your job when you're doing organic reaction methods. And there's another resonance structure for this. Where we stabilize that carbonyl-carbon by donating from the ferrous electron hydroxide. So given Great Rule of Organic Chemistry number 1 hasn't been applied, would you like to revise your answer? Where you said that the alcohol, it's not an alcohol, right? It's carboxylic acid. So
Oh,
you said the OH here was going to attack something. What's the most nucleophilic oxygen in this molecule?
Like the molecule with the aromatic
Which of
ring.
these two oxygens is the better nucleophile?
Oh, the one that we just, the resonance one where you have the
So
negative.
two of the three resonance structures have a negative charge on that oxygen.
Yeah.
One of the three resonance structures actually has a positive charge on that oxygen. So the nucleophilic oxygen in a carboxylate or even a carbonyl group is always the doubly bonded oxygen.
Okay.
It's true that this is the one you're going to get rid of. We're trying to get rid of it in the end, but that's not the nucleophilic oxygen. And we'll see that when we do the attack too. Because the intermediate that forms when we use this oxygen for attack is resonance stabilized, and the intermediate from that oxygen attacking is not. So it's this oxygen that's going to attack this carbon. Because chloride is not very good at donating electrons in to form this more stabilized material, this has a larger partial positive charge on it than that one does. So the attack will be from the nucleophilic high bond or the lone pair. It doesn't really matter which one you show. Generating a tetrabutyl intermediate.
And that's irreversible.
No, that's a equilibrium. You can always keep the nucleophile back up. And you'll notice that this positive charge is now stabilized by resonance. And I could have gotten directly to that intermediate by using this pair of electrons to push the double bond over.
Oh.
That would be true.
That's
If I-
kind of what I was, not exactly, but kind of.
If I use this as the nucleophile, it is your usual first impulse. Right? If I use that as the nucleophile, the intermediate can look like this. And that positive charge can be stabilized by resonance. It's actually adjacent to a carbon that has a partial positive charge. So this is an unfavorable intermediate. And that oxygen is not going to be the one that's acting. What's the second step?
Well, considering you already drew that arrow.
So what's step 2 from this intermediate?
Oh, the arrow was just to show that the.
This is just resonance.
No, the one on top we drew the arrow.
Oh, that was just showing resonance.
Okay, never mind.
So what's the second step?
I would bring down the electrons on that to form a double bond and get the chloride to leave.
Loss of Legion group. Because the first step is nucleophilic attack, and the second step is always loss of Legion group. because it was a neutral nucleophile, our product of that acyl addition elimination is still positively charged, and we need to make it neutral. Somebody's going to take that proton off. Who's going to take that proton off?
Well, not the chloride. I can
Not
do
the chloride.
that.
Probably another molecule of acetic acid. Because this oxygen is still.
Okay. Does it matter like which resonance structure we work with?
It's customary to work with resonance structures that don't have unfilled octets. So it's most common to show the resonance structure where things have filled octets, but so it doesn't really matter. You could have gone from here, kick this out, and come up with that resonance structure, and then we could use acetic acid, take that hydrogen off, and regenerate the double bond in that step. Doesn't really matter. The reason why it makes more sense to use acetic acid as the base to take that proton off in the last step is twofold. One, we're probably running this in acetic acid as the solvent, so we have a lot of it. And two, the pKa of the protonated acetic acid is a couple of orders of magnitude less than the pKa of HCl. So if you dissolve HCl gas in acetic acid, it's not quite fully dissociated like it would be in water, but it's still mostly dissociated, because the reaction of HCl plus acetic acid, or benzoic acid in this case, to form the conjugate acid-base pair. That equilibrium constant is probably about 10. Because you're 2 orders of magnitude less acidic as the protonated acetic acid than you are as HCl. But it's the same mechanism, right? Nucleophilic attack, loss of leaving group, proton transfer, and now we have an anhydride. So if you know the mechanism for one of these, you know the mechanism for all of them. Nucleophilic attack, tetrahedral intermediate, loss of leaving group, positively charged intermediate, and then proton transfer to generate neutrality. So we've gone through the reaction of a unreactive acid derivative with a negatively charged basic intermediate, or basic nucleophile. And we've gone over the reaction of a reactive acid derivative with a neutral nucleophile. And they're similar. They both have nucleophilic attack followed by loss of leaving group followed by proton transfer. It's just a matter of whether the intermediates are negatively charged or neutral. Positively charged or neutral. It's possible to take a reactive acid derivative and react it with a basic reagent. It's just not necessary. You could react this with sodium methoxide in methanol solvent, and you would do a nucleophilic attack. Forming a tetrahedral intermediate, followed by a loss of leaving group. From your product. But you don't need sodium methoxide to do this reaction of an acid chloride to an ester. The acid chloride is capable of reacting with just neutral methanol. difference between these two mechanisms is when we start with the negatively charged nucleophile, we don't need a third step because our product of the second step is already neutral, whereas when we do the reaction with the neutral methanol, we need a third step. What's the base that's going to take that proton off to generate neutrality?
The methanol.
Extra methanol. Right? So we always have a second equivalent of alcohol in here. And that's because HCl is a strong acid in methanol as well as in water. Methanol and water are functionally equivalent. So HCl would be completely associated in methanol to form the methyl ion and chloride. So it's possible to use a neutral or a negatively charged nucleophile. It just isn't necessary. So the third mechanism that we need to talk about is when you have an unreactive acid derivative and a neutral nucleophile. Those reactions will not go spontaneously. Those are the ones that have to be acid catalytic. So we're going to take a break, and then we're going to come back and we'll talk about the mechanism for unreactive acid derivatives and neutral nucleophiles under acid catalysis. There'll be more steps because there are always more steps in acid catalyzed mechanisms than there are in base catalyzed mechanisms. So I'm going to save this video, we'll take a break, and then we'll come back, we'll have about half an hour to finish up. I also need to explain why some acid derivatives